My name is Johnny Sjöberg. I'm the CEO of ITASCA International. I feel both privileged and happy to be part of this event. Now I have the great pleasure to introduce the first keynote speaker of the symposium, Professor Emeritus Charles Fairhurst. So Professor Fairhurst can rightly be called one of the founding fathers of the discipline of rock mechanics, having established the research area at the University of Minnesota in 1956. And ever since, he's been one of the major contributors in the world to the development of rock mechanics. Always seeking new knowledge, always advocating for the increased use of the underground space as a resource. There's also a book published on Charles called A Long Shadow. Well worth a read if you haven't done that. The list of publications in this book run for 16 pages. What I find even more fascinating is the PhD tree of Charles Fairhurst. This lists all the PhD graduates of Charles, their respective students that have earned a PhD, and so on, up to 4 generations deep. It's truly an amazing list of people. And many of these are now famous, world-renowned in their own names. As you probably know, Charles is also one of the founders of ITASCA. We've been around now for more than 40 years. We celebrate our 40th anniversary in 2021. We have offices and code resellers all around the world. We combine consulting, software development, and research. It's only appropriate that we have Charles present the first keynote of this symposium. Please join me in welcoming Professor Charles Fairhurst.
Well, thank you. I had a host of material in trying to look at this talk, but obviously when it was limited to, I'm not sure it's 20 or 30 minutes, 20 minutes or so with time for questions, I had to cut a lot out. But I put it into the appendix, which will not be shown, but not be discussed, but it will be available to you. I should also mention that actually, before coming to Minnesota, my original intention had been to do a degree in applied mathematics, but for certain reasons of serving in a national service, so-called, after you graduate from high school, I went and did actually 3.5 years in underground coal mining, during which period I also worked on a degree at the university and PhD. So I came to university with a knowledge of the real problems being faced by people in mining as well. So that has sort of conditioned a lot of what we've done since then. Sorry, let me just, that's the title of my talk. It's by David Attenborough, and as you know, it's a lot of that opinion is shared by the United Nations, everybody else, that it's remarkable how serious this is, but at the same time, at the bottom, you see, they say this idea of going to net zero emissions by 2050 will fail without a supply of critical minerals. And I'll talk a little bit about that. This is a quote from the master's degree thesis of one of our students, Enrique Chacon, who was the vice president for development and innovation for Codelco Chile. And in a way, that's his expression of what you really mean by innovation. You may not solve all the problems yourself, but do enough to try and make it so that somebody else can have advance on it. And I have to say, sadly, that his master's degree was awarded posthumously because he just about completed it when he died of cancer. A wonderful loss, a wonderful person and an awful loss. You'll see that in some of what I'm talking about. Okay, that's the title. I have to also mention that, of course, quite a bit of my recent experience has been in the United States. And it should be known that the term critical mineral has 2 definitions. The first definition was actually about 15 years ago now by a National Academy of Group. And it was a question of that a critical mineral to the United States was a mineral that was essential to the economic or national security of the United States. And the US tries to pride itself on having a sophisticated military, and that's what they mean by national security, and that it has a supply chain vulnerable. But where, if you go to the World Bank or to the International Energy Agency, a critical mineral is something to help the move towards clean energy technologies and away from fossil fuels. So these two are not identical, although there is some overlap. And there you'll see some references to where that phrase is. Next one. So right now, the United States Geological Survey was asked by the government to define how many such critical minerals there were in the country. And they said that they found that there was 100% net import reliance for 12 of the 50 that they defined. And there's a reference to where the 50 are. And they were more than 50% net import reliant for an additional 31. So, and as people know, that China is the leading producer for 30 of those 50 critical minerals. They let people mine them around the world, but then they ask them to send the raw rock to China, where they will do all of the processing. And of course, anybody in the world, they want processed materials. They don't want the stuff that comes out of the mine. Next one, please. This is a summary of some of the problems facing the mining industry. That is a plot on, it's not quite a logarithmic scale, but it's from the last 2,000 years of the world population. And you can see just what happened at the Industrial Revolution. Now, it turns out that the increase in population was actually a consequence of advance at that time of medical technology. And it wasn't the fact that minerals were being mined, but the two coincided. And right now, 85% of the world population is listed as being in developing countries. Now, this does not mean backward countries. I mean, China and India are listed in developing countries, but the point is they're trying to improve their standard of living. And so it's known that the demand for minerals increases 4 times faster than the increase in population. And as a quote there from C.P. Snow, that technology is a queer thing. It brings you advantages on the one hand and stabs you in the back with the other. And there's no doubt that the development of the Industrial Revolution brought along a great deal of advances, but only recently have we learned that there are also tremendous disadvantages. And some things are not commonly known. There was a lot of opposition to some of the fertilizers that are being used in agriculture, but it is now known also that without those fertilizers, the world would only be able to support 4.5 billion people. So you have a difficult choice. Do you want to allow the population to grow or keep more people living, or do you want to cut back? So there are some not so simple questions associated with the critical minerals issue. This is a picture from, I got the data from Our World in Data, which is a very reliable group at Oxford University. And here you see, over the past 20 years, how far have we moved towards a reduction in the use of fossil fuels? And where did that reduction come from? And at the bottom, you'll see that over the past 20 years, the US has reduced its reliance on fossil fuels by 6%, and the world by 4%. Now, in order to achieve net zero by 2050, we're going to have to get to 45% reduction by 2030. Now, that's 6 years away. That's not very realistic. And the other thing that I want to mention here is that nuclear power, and some of the states is a bit startling, is as safe as wind and solar when it comes to how many people have lost their lives as a consequence of the use of that. Now, remember, this data includes Hiroshima, Nagasaki, Fukushima, and all of that. How many people actually died over that period of time? I find it a little startling myself, but it does say to you that the real concern for nuclear fuels, nuclear power, is declining somewhat. It's very reliable, and it's, as they say, available 24/7, whereas wind and solar are somewhat intermittent. But if you look at the Some of these are not growing because, for example, in the United States, hydropower, they are actually taking out dams that generate because there's an objection environmentally to the use of dams. And so again, I say that the chances for reaching net zero by 2050 are, in my view, small. And it's shared actually by a number of other people. Minnesota, I should say, and that's where I'm from, has actually done quite a bit better. You see, it's actually got renewables are up to 31%, with a big chunk from wind. And yet the other point is, of course, that Minnesota accounts for only 1.7% of the population in the United States, and a lot of other areas are not doing as well. So what are the challenges to achieving net zero by 2050? And this is from Deutsch, who was for, I think, President Biden. He was sort of science advisor and actually at one time the CIA director. He's a physicist. And he said, achieving net zero 2050 does not assure complying with the global warming temperature ceiling. The US might achieve net zero by 2050. The world almost certainly will not. For the US to achieve net zero 2050 requires a massive transition of the economy, which is extremely unlikely. A lot of people stick to what they're doing now and don't like to change. And I saw one quote saying, why is the public so apathetic about this? And somebody said, well, the trouble is that CO2 is an invisible gas. If it was a dirty, smoky thing, the public would be up in arms to see how much is being released. So, so my view is that while everybody should make every effort to achieve global net zero by 2050, we should certainly continue working on that. But it is prudent to consider the option in case that goal is not achieved. This is what NASA has proposed. Actually, it's a Professor Hollander, who's an architect, looking, and he enjoys the idea of creating new cities from nothing. And so he decided to write this article. It's in the New Scientist, I think, called How to Build the First City on Mars. And you notice it's entirely underground. The surface is not particularly attractive. I think the Earth has a lot more to offer than that. And in a recent talk in the National Academy of Engineering about, I think it was 50 years or so after the Apollo program, Dr. Bolden, who was himself quite a good scientist and a former administrator of NASA, he said, long-term survival on Mars is a major challenge. I'm a big fan of the underground. Well, that means that the radiation on the surface would mean that you couldn't survive. And things that I didn't think about. But apparently, if you also in low gravity environment, which you have on Mars, it can affect your bones and your joints and so on. And I have enough of trouble with that now on my here. I don't know what you would do on Mars. So it says to me, why not think about if you're going to do that sort of environment? By the way, everybody's living there and there's solar, there's light coming through into an underground. I recommend that you look at that reference on the right there, because Hollander himself makes some very fascinating comments about what that would look. And by the way, in some of this product, in the copy of this, it may well be that when you click on that, you don't get to the link. But all you need to do is copy that and put it into Google, and you'll have the link right away. I tried to make sure that they'll all work, but I'm not sure I'll make every one. And so now in Sweden, there have been quite a bit of work done on underground, design for underground. And the origin of this was that during the Cold War between the United States and the Soviet Union, people in Scandinavia got a bit concerned because they said if anything starts flying from one country to the other, maybe some of it will come out and it will hit us or affect us, certainly. So they felt they'd get involved. And they were neutral, but they decided to look at what was the potential of the subsurface in alleviating some of these issues. Obviously, one thing, if you have radiation on the surface and you were able to stay underground for, let's say, a week or so, maybe that will pass. And there was a great deal of thought given to it. And recently, for example, if you looked at what was happening in Ukraine, one of the first things that the Russians did was bomb going after nuclear power plants, going after oil storage and so on, because without that kind of energy, your army or whatever it is there can't operate. And so I could go into a lot of detail about how much work has been done by Sweden in making the underground look attractive. And I can say that there's a great deal of work done. And there's a book called Going Underground, and which I had a copy of. And I asked the Royal Academy of Sweden recently if I could get some more copies, and they said, sorry, it's out of print. But I'm a member of the Swedish Academy, and so they gave me permission to publish the book, make a copy of it, and that's available to you if you wish. It's about almost 200 pages long, but of all of the things that they thought of in Sweden that to make use of the subsurface. I remember taking a group of Minnesota legislators to talk to the Swedish legislators, Stockholm, and one of the Minnesota people said, why do you put your sewage treatment plants underground? And the Swedish colleague said, well, that's where the sewers are. Why bring it back to the surface to treat it? And there are many, for example, if a subsurface one, the environment is constant 12 months a year. And if you're trying to deal with a biological treatment of material in sewage treatment plants, it works much more efficiently year-round than adjusting for summer, winter temperatures. There are a great deal of things like that. So more recently, and Johnny advised me of this, in 2018, there's another book being produced called Sweden Underground, Rock Engineering and How to Benefit Society. And you can order that, and there's details there of how to order it. And I have a copy of the book. It's wonderful, and it talks about, like, we built an underground civil engineering building at the university, and I've had colleagues go down there from other men, and some have said, we find it a bit depressing. There's no external light things. That is a big problem. You have to know how to make the subsurface welcoming and so on. That's all dealt with in that book. And I think you can see that what I'm saying is, well, I'll jump forward. When ITASCA was formed, the person who was spearheading that whole thing for Sweden was Magnus Bergman. And Magnus was a co-leader with John Markham of the first ITASCA group. What happened for a while, underground was okay, but then it was actually the OPEC oil embargo that triggered that. But then that left, and the interest in underground space disappeared too. But I think it will come back as a preference to trying to go and throw a few people on Mars. This is something that was in there as an example. We're talking about storing nuclear waste. And a couple of people came up and said, why don't we make an analog subsurface of something like the Faraday cage that's used in electrical to shield the interior? And what they wanted to do was put a series of vertical boreholes and pump from them to try to create a barrier of groundwater pressure. So there would be depression there, and water would flow into it from one side and also into it from the other. Now then, it didn't work because the holes, and I've shown a copy of them on the right, were too far apart. And it was a simple matter to look at how far you could depress the water table. But I wonder if this research can be done, for example, using shaped charges to try to create a reduced zone. Now, it's a long shot, but in that you could possibly think of certain types of mining where you're using aggressive chemicals like acids to extract minerals, but keep it from going outside. So that's the kind of stimulus you might get from reading that book. Another thing that I would like to discuss more with colleagues in ITASCA is the number of projects that ITASCA has done, and I've talked to some in Australia, for example, who tell me that, my God, if we could only be allowed to publish what we've done, the world would have a much bigger, better, much more informed impression of what ITASCA does. But when you're working on a project with industry, very often the lawyers move in and say, sorry, you're not going to be able to publish that. But usually there's a limit, 4, 5, 6 years, whatever. And that, by which time they can have patented everything. But this was something we did for Fairhurst on rapid tunneling. And it was different than the usual in that it only used 4 cutting arms. One cut a saucer shape. And by the way, the person who did this analysis was Branko Demjanic in the Minneapolis office. And it cuts like a saucer shape in the middle. And then the other 3 arms go around and cut it to the outside. And they were saying, oh, we're breaking the rock in tension and not in compression. And sort of hinting that that was a lot easier to do. Well, what I show on the right is one slide showing the standard way of a roller cone bit. And I say you can even see by the shape of that stress distribution that the rock didn't like it. It doesn't look very pleased. The one on the right is what happens when you cut in the other manner. And it's true that you do break that. You see that large blue, the blue line going towards the free surface. That is broken in tension, obviously. But the interesting thing that we found out is that once you've broken it, you're left with that geometry of a curvature. And you start with a right angle situation. In order to get down to the next right angle to have the break in tension, you spend 93% of the energy crushing the rock in extremely fine particles. And fortunately for us, the people at Fairhurst tested this out in a real case in the Ruhr sandstone. And if you look, you see on the right that it's indeed true. There are a lot of big particles and a lot of very, very fine particles. But there are some interesting observations. We were cutting to a depth of about 6 millimeters, and an analysis showed that you could go to twice that, and the forces didn't go up very much. So is this a lost cause, or is there something that could be done? Unfortunately, we weren't allowed to publish this, but we are now. And so I think that throughout ITASCA, if we could look at what have people done, and if necessary, contact the company and say, do you mind if we publish it now? Because if you go back to what Enrique Chacon said, maybe we didn't come up with the right answer, or maybe we didn't solve the problem, but maybe somebody else will. And I think that's one thing that would be nice to do now. This takes me back to when I was actually working underground, and I was part of a program where we were told that we were being trained to be future managers or whatever. So if there's something ever going on in the mine, the manager was instructed to get us and go and participate in the experiment. And this was a very early test to try to see if you could use burn cut, drilling 9 holes to the center of a cut and blasting them simultaneously, with the idea of crushing that rock in between it, and it provided an internal free surface for future breaking. And so we went to do and look at this, and the manager said, well, put a steel sheet up there, because if that doesn't work, it's going to go flying down, all that's going to go down the tunnel. Well, it didn't work. And what happened, that steel sheet telescoped about 12 or 15 of those there. And you can imagine the manager wasn't particularly excited about that, because it's going to be a hell of a lot of work to fix that. And that's something that I've carried through with me, that we have to, at least if you're doing modeling or whatever, and I think there's a major room for modeling, but we need to be able to present that in a form that the management or the actual people can see the benefit of it, and not just be shown all of this, because they have many, many skills, but they're not necessarily modeling. So I've always had an interest in this problem of blasting since. I'm asking this, what's the optimum distribution of blast hole diameters? And while I'm on the top, while I mentioned Atlas Copco, one of my first presentations was to a group when Atlas Copco convened blasting people from around the world, and mine managers and everything, said, we just want to know for the future, what is the optimum hole size that we should be designing for? I mean, it was just a basic question. Should we have small holes easier or big holes easier? And what I know is that if you model this without discontinuities in the rock mass, you will see that you don't really need a central bore because the rock does not expand. The expansion that comes, that you get a 30% expansion of the gross volume after a blast. It's largely because discontinuities, three-dimensional discontinuities in the rock control, because not everything breaks to a fine point, it just moves and creates void spaces. So we need to have a model like this, and I've talked to Jason Furtney, and he says, yes, we can do this. It's not a problem, but it's going to cost a couple of $1 million to do the real work. So who's going to step up and spend that? So here is if you like, a solution waiting for funding, because I think it would be fascinating to see, are there if you want to drill more than one diameter forward in a tunnel, you really need to have long parallel holes, but they can be larger diameter. And when you're detonating something, it works much better if the diameter is large than if it's small. So what is the optimum distribution? Should it be 2 or 3 different sizes, not necessarily one in the middle? I don't know. So I would like to see if we could get somebody interested in doing that. This is back to the question of, now not back to, but to a question that's plagued mining for many, many decades. This is the Kola gold field in India. And at the time, it was on a par with the Witwatersrand for the deepest mines in the world. And it was designed, actually, I won't go into it was designed like an elliptical, because somebody said, oh, if we have a vertical stress is higher than the horizontal stress, and they thought it was about 1/3, and we should design a tunnel that's got the similar dimensions, 3 times higher than wider. Well, they tried it, and on the right, they had a rock burst, and that's what you saw afterwards. As you see, it's a bit tricky. Now I come to something that was recently done by somebody known to all of you. It's actually a Hecla mining company in the Idaho, but they came up with a new mining method, and they were trying to deal with the constant problem they have of induced seismicity and rock bursts, and it was really hurting production. But this team, led by Mark Board, who worked for over 25 years for ITASCA, but then went to serve as a vice president for Hecla, he came up, this was the method on the right, on the left, is what they were using beforehand. And there you see, for example, a fault, just they're excavating, they're stoping downwards, and there's a region of rock that below the stope where they've excavated, which is yielded. And so stress concentrations are going somewhat below the stope, but not particularly far. And there's a fault, a presumed fault there. And so that could very well burst and cause damage in the stope. Well, what Mark did, in my view, and he has given the paper and he'll tell you something different, but in a simple term, he scaled everything up. And he got involved with a mass blasting of the stope, going down, as you see, quite a long, long way. And so the stresses went down below, but the workers were going to be up on where you see the top cut. And the blast was such that it triggered any seismic, potentially seismic release below during the blast. And they have found that it is production has gone up. It's the deepest mine in North America. This is now about over 2 kilometers deep. And the top paper, by the way, gives a paper by Mark Boyd and others, the very top layer. That'll tell you the details. But what, in essence, in my view, they're doing, they're placing a cocoon of de-stressed rock, because there's no stress in the open pit that's de-stressed by being an opening. But below it's blasted and there's an opening there. He's driving the stresses farther away from the operation. And as a result, to date, their production has increased, I said about I think 60%, because they had a lot of time. They had to keep the miners out of the mine until the bursting had subsided. So this shows to me, and I think I know, I won't go into the detail. I think I know of mines around the world where they have been closed that you could very well have a look at with this method. So that's, and that came from, if you like, ITASCA thinking. This is something else. In 2015, the Society of Mining Engineers had a conference in Denver, and it's called The Future of Mining. And one of the people on the panel was Gwen Hendricks, who was the vice president for innovation and technology at Caterpillar Tractor. And Caterpillar, I don't know if you know, their research division has about 1,000 PhDs. And this was what she said at the end of her talk: we may see an unmined mine in operation within the next decade. Now, it's not happened yet, but is it really a possibility? And I've had discussions with colleagues, and they say, no, we can't get away from the fact of having somebody on a caving operation looking and operating the machine right there. Because if there's a big block comes, we have to stop and blast it. So I said, but maybe what you can do, you can get the same imaging of that, what the operator is seeing, up at the surface. Because once you're down below, you cannot transmit signals except hardwiring them to the surface. But once you do that, you can operate that mine from anywhere in the world. You don't have to be there. And they've shown that with the transportation, which is what this young lady is doing, controlling transportation. So I think you're on the cusp of a potential for an awful lot of innovation. And we say, well, maybe that's not what ITASCA does. But people can tell me from Minneapolis here, but about 2 or 3 years ago, there was a bad accident where a tractor was carrying a wind turbine propeller of the blade very high off the ground, and it was going over soft ground towards where the wind, and it tipped over, and the operator was killed. And ITASCA was asked, ITASCA Minneapolis, can you design for us a system so the operator can see ahead where the soft ground is and where the hard ground is to avoid that kind of thing? And they did it, and they got the prize for innovation for the local area. So that talent exists in Minnesota. So if we get thinking a little more about what can you do to help reduce the exposure of people, this is what I said recently, looking the Rock Mechanics Symposium. The first one was April 1956. And I looked at, and NASA was established at the same time. And I looked at how far has NASA come on that period of time. Well, if you look, in September 1977, Voyager 1 was launched. It is now 24 billion kilometers from Earth, but it's still sending radio signals back to Earth. And in 2018, the two halves of the James Webb telescope were joined remotely in space. They put them together, and that was, I think, about 1.5, I think it's 100 million miles from Earth was where that operation was done, remotely. Now, I look back at what had happened in mining, and things that kept coming back to me was the Chilean mining disaster in 2010. And the details are there, but the men were trapped for 63 days. They were not found until 17 days after they'd been underground. Now, anything happening on the surface, you wouldn't have those links. You can't transmit those signals through the ground. So maybe what you really should be trying to do is avoid the exposure of the miners to that. And so do your best to keep most of the operations above ground. That on the right shows the president of Chile, how they found out that the miners were there, was they drilled a hole and it drilled into the cavity or into the refuge area that the miners were in. And one of the miners taped that message to the bore, to the drill. And when they pulled the drill back, they saw it and said, oh my God, they're there. There was no communication by radio or anything. So that's the challenges of the subsurface environment. But they are things that today maybe we should be looking at, and I think ITASCA could very nicely try something. Another thing I would like to do is say, what other things can we think of? The National Science Foundation has had a program for engineering research centers. They've had 75 so far, and they fund them. And it's a joint thing between universities and others. And they require about $5 million a year for 5 years minimum. And at the end of that time, they're evaluated and perhaps extended for 10 years. But so far, they have established 75 R&D centers throughout the United States. Not a single one has been in rock mechanics or underground engineering. And I think it's about time that the industry stepped up and that the university stepped up. And I think people at ITASCA, and I mean around the world, have a lot to contribute to that. And I'm not anxious to do much more work at my age, but I'd like to work with somebody to design something, telling them that now, for the first time in certainly my lifetime, mining is seen as an essential component of any future life on Earth. So that's the level of concern we should have. It's quite interesting to me that now the presidency of ITASCA is with Johnny in Sweden, because as I've said before, Sweden has been the most innovative and creative group that I've met, although there's Australia and others are doing good work, and the Canadians. Okay, Paul. So one of the biggest problems facing the mining community certainly have been the tailings dam failures, which have resulted in dreadful loss of life and so on. And I know that personally from 1966 in Aberfan in Wales. And I was actually part of a group looking at this when a coal mining tailings dam failed, and it came in Wales. These are small village communities, and they at the time were very isolated from each other. They didn't move around a lot because it was hilly between, and so they had one school, one grade school, and a small community. This failed, and it came right down over the school, and 160, every child in that school was killed. And that was a community, that was an entire generation of children for that community. So it was horrible. Right now, Anglo-American has introduced this hydraulic dewatered stacking, and they have shown, and it makes eminent sense when you see it, all that they do, they stack so much of the tailings, and then they stack sand and another and that way the sand can avoid the buildup of pressure. And that's industry now. So industry is doing this. So I think ITASCA has a great, I mean, I don't know if they've optimized this yet, but I talked to Christine de Tournay and she said, oh, that's easy. We can do that. So the communication with the companies is going to be imperative. And I just hope everybody does that. I took out loads of material, some of it including the experiments in the Pinawa area where Paul Young and I worked closely together for many years for radioactive waste and sort of things like that. I had a lot of other topics that I had to cut out. So you can see them all on there, and I put explanatory notes in with them. They're not very logically ordered, but you might get an impression from some of them. So thank you very much again indeed.